Okay, so now that we've established that the estimated standard error strongly resembles the old standard error that we used in Chapter 8, let's go on to something else. So let's define it. The estimated standard error is used as an estimate of the real standard error when the value of the population standard deviation is not known. It's computed from the sample variance or the sample standard deviation. And in our case, I really will always give you the sample standard deviation, and provides an estimate of the standard distance between the sample mean and the population mean. Finally, you should recognize that we have shown formulas for standard error using both the standard deviation and the variance. We concentrated on the formula using the standard deviation. At this point, we shift our focus to the formula based on variance. And really, I don't do that. I have to acknowledge what your text says here, but I will always stick to this formula. This one's equivalent. If you were ever given the variance, you could just plug this in, but I strongly prefer this one. I really do. So anyway, it's a fine distinction, but I think when we're in the first vestiges of learning, the first salvos, I like to take the simplest formula that we can possibly render. Okay, defining t obtained. This is not z obtained, but it's going to be a t obtained. The t statistic is used to test hypotheses about an unknown population when the value of the population standard deviation is not known. That formula has the same structure, and you're going to be pleasantly surprised, as z, except that t uses the estimated standard error, and here we go. The first thing I do, if I happen to be given the variance, is just take the square root of it to get the standard deviation. Although in our cases, I'll always give you lowercase s, so you can almost just skip this part. Then I'm going to plug that sample standard deviation into the numerator here, and of course take the square root of n as the denominator for the estimated standard error. And here's t. T is almost precisely the same as z, except we're substituting the estimated standard error into something that we'll call the t distribution. So now we can substitute that estimated standard error, and the result is this t statistic. Piece of cake. Really the same process. And again, I'm cutting a third of this out because I'll always just be giving you this. There won't even be the square root to take. So there's something else though, and I sort of warned about this in the first video. We got used to z critical by using the tables. Now we're going to use t critical. And the calculation for degrees of freedom is n-1. In this chapter, we've introduced the t statistic as a substitute for z. The basic difference is that the t statistic uses sample variance or standard deviation, and the z-score uses the population variance or standard deviation. To determine how well a t statistic approximates a z-score, we must determine how well the sample variance approximates the population variance. And the way that's done is with degrees of freedom. To your text's credit, they go on a little bit about this, but I never ask about it on a test. But for the sake of completeness, I feel like I should mention this. In Chapter 4, we briefly introduced the concept of degrees of freedom. Reviewing briefly, you must know that the sample mean before you can compute sample variance, this places a restriction on sample variability so that only n-1 scores in a sample are truly independent and free to vary. The value n-1 thus is called degrees of freedom for the sample variance. For our purposes, I'm merely going to have you calculate the degrees of freedom as n-1 in a problem, because that'll be necessary to interpret the tables that supply the critical values of t, as we'll see. So if we had 16 participants or 16 mice or 16 pigeons, the degrees of freedom will be 15, 16 minus 1. That's most important for our purposes. So a t distribution is the complete set of t values computed for every possible random sample for a specific sample size, and it varies by sample size, as we'll see, unlike z, or specific degrees of freedom. The t distribution approximates the shape of a normal distribution. Now, this is where it gets a tick tricky, but we'll walk through this very slowly, and it's really not a big deal at all interpreting these tables. And by the way, the tables are scanned in on D2L under the appropriate module there. They're on the bottom right. So this t distribution is a complete set of t values for every possible sample. Now let me take that back. This is a little bit of a fib. Some of the higher values are omitted, as you'll see. And when we omit a value, we go down to the next one to substitute for it. But we'll get to a couple problems that betray that.